In our survey of analytics topics, it's important to discuss the concept of big data. Now, you've probably heard that term before, but how would you describe it? How do you know if you're actually working with big data? By the end of this video, you'll have a better grasp of what big data is, and you'll also understand why it's a game changer in the field of data analytics. Let's start with the basic definition. Big data refers to data sets so large and complex that traditional methods will struggle to handle them efficiently. Well, that's a good start, but there's a lot of subjectivity in that definition. So we're going to break it apart and separately discuss what are known as the 4 V's of big data. You can think of them as 4 factors that help us understand the scope and challenges of working with big data. They are volume, variety, velocity, and veracity. You'll want to be familiar with each of these terms and how they help illustrate what big data is. We'll start with the obvious quintessential characteristic of big data, its volume, or the size of the data that is being managed. But this dimension begs a question. How do we know when a data set is sufficiently large so as to be considered as big with a capital B? A short and cynical answer is, there is no answer. It's all relative and the goalposts are always changing. But we're better than that answer. Let's give the topic a little more thought and see if we can't find some useful insight. Here, we've got a table that describes various prefixes for data sizes and how each compares in relative scale to the previous line, each being roughly 1,000 units of the preceding. Now, part of data literacy is being familiar with how data size is measured and having a grasp of data scope in the modern environment. So I would like you to be able to recognize the name of each of these prefixes and how they rank on the scale. You're probably already familiar with the first half of this table. Many of the files stored in your computer are measured in terms of kilobytes and megabytes. Some of your larger software files, or maybe an entire movie, might eclipse 1 gigabyte. And it's likely that the laptop or computer you're using to watch this video has a total storage in the single-digit terabytes. Now, once we cross into petabytes, we could perhaps consider ourselves as entering the realm of big data, at least today. The capacity of data centers for cloud storage platforms will likely be measured in petabytes. Exabytes describe the data requirements of the world's largest tech corporations, and zettabytes is the term currently used to quantify all of the data in the world, where the entire global data sphere can be measured in the hundreds of zettabytes. Now, knowing the term yottabyte, that's as far as I'll take you in this class. And for now, yottabytes is a theoretical storage capacity, as in potential future global data storage. Now, let's keep adding color and context here by discussing changes in data storage needs and costs from the perspective of the average consumer. Now, the Apple II computer in the 1970s really didn't have any internal storage. If you wanted to do anything, you had to rely on external memory. We've got this 5.25-inch floppy disk. For $10, you could buy yourself external storage ranging in about 140 kilobytes. Looking today at Walmart, you could buy a flash drive, 32 gigabytes for $5. And an external hard drive, a whole terabyte, you can buy today for about $70. With these figures, an external hard drive is literally, almost exactly, 1 million times cheaper per unit of storage. Well, that's all well and good for an average consumer, but how has data volume changed for large corporations? Well, let's take the largest data producer of them all and examine Google and how it has changed from 2004, back when its logo was this beautiful image on the left, to the present. Now, just for fun, pause the video and take a guess at the scope of Google's data storage needs roughly 20 years ago, as well as those it has today. Okay, back in 2004, Google's primary storage needs related primarily to its index for the search engine. But there were also Gmail accounts, about 1 million of them, whose emails and file attachments had to be stored somewhere. These storage needs mapped to the hundreds of terabytes. Now, since that time, Google has added a variety of data-intensive services to its business, like YouTube, Google Earth, and Maps, and various data storage platforms. Each day, the company and its users generate hundreds of exabytes of data. Anyway, I hope that this gives you a sense of the ever-changing standards for what big means in terms of volume. Now, part of the reason for the exponential increase in the volume of data is the rise in the variety of data types that we can now collect and analyze. One way to describe this is that we've moved away from only structured data to also collecting and analyzing unstructured data. Structured data refers to data sets with a fixed schema, a standardized format. Think of tabular data like Excel spreadsheets or relational databases. We're working with text and numeric data types with the primary benefit that the data easily is organized and searched. And a structured format still constitutes the primary way that companies store data. However, the landscape is evolving, and the ability to harness the potential of unstructured data is becoming increasingly valuable for gain insights. I'm talking about analyzing data from social media, images, and video, and many others. While it may be more complex to analyze, there are powerful ways to extract real value from unstructured data. Now, variety can also refer to the diversity of sources from which organizations can collect data. We live in the age of the Internet of Things, or IoT, which refers to the wide range of devices and applications that continuously collect various types of data. IoT devices are pervasive in our daily lives. We've got smart appliances like thermostats, security systems, even smart fridges. There's the whole wearables industry, where we've moved from just tracking the number of steps we take to also collecting data about cardiac health and sleep quality. I've got family members with diabetes, and they love having continuous glucose monitors to provide blood sugar readings in real time. If you drive a car that is connected to the internet, you'd probably be surprised about the kind of data that is being tracked and stored even locally within the infotainment system. So not only are we collecting and analyzing a variety of data types, we're also expanding the variety of sources of data. Well, if we've got a lot of data, it does us no good if we're unable to actually retrieve and use it. Hence the importance of the ever-increasing velocity or speed with which data is processed and analyzed. Processing power is constantly increasing. Every 2 years or so, the number of transistors on a microchip double with minimal increases in cost. And advances in processing power, that's been critical to the rise of AI applications, like large language models. They rely on vast data sources to be trained on. But we're not just processing data, we want to extract value from the data by analyzing it. So sports teams, such as those from the NBA, spend millions of dollars just on their analytics function. Now, when we use the term velocity, I'm not just talking about looking occasionally at box scores and player stats. I'm referring to teams analyzing real-time video in the middle of a game. Cameras are recording every movement of the ball and all 10 players 25 times per second. This turns into millions of rows of data that are passed through high-powered statistical models, all to be able to give insights to a coach to make tactical adjustments at halftime. We're informing strategy and trying to mitigate injuries. That's fast processing and analysis. Another important example of high-velocity analysis involves institutional investors and equity markets. From the time that public companies release value-relevant info to the time that trades are being executed, that can be measured in a matter of seconds. Hence the need for effective data extraction processes and fine-tuned valuation models. There's a lot of money to be gained from being a first mover. And this is why we're able to have theories about semi-strong efficient markets, because investors are trading on information almost immediately as it is publicly released. The last of the 4 V's is veracity, which refers to the reliability and accuracy of the data we collect. Since we're dealing with massive data sets, we have to be innovative in applying techniques to ensure that the data is of a sufficient quality. Later in this course, we'll review specific characteristics of high-quality information and the importance of each. For now, we'll just stick with the need for the data to be accurate or free from error. You'll want to be familiar with the term garbage in, garbage out. This essentially means that the quality of your output depends on the quality of your input. If inaccuracies are introduced in the data at the collection or processing phase, then the insights you gather in your analysis will be useless or misleading. Big data is a buzz term. Some people use it without really knowing what it means, But you are now better equipped to use the 4Vs to describe big data. They are volume, the sheer size of the data. I want you to know the prefixes used to measure data size and how they stack up to each other. Variety, the diversity of data types and data sources. Know the differences and relative advantages of structured versus unstructured data. Next, velocity, the speed with which data needs to be processed and analyzed. And veracity, which gets at the reliability of the underlying data. If the data coming in is garbage, you're limited to finding garbage insights from your analysis. And one final note, big data is powerful. If you're able to check off all these previous boxes, you've got a wealth of insights at your fingertips that could potentially add significant value to your organization.